Okay, well, good afternoon, everyone, and sorry that I wasn't able to attend in person, mainly because of the teaching schedule. But before starting, I want to acknowledge and thank my postdoc, Dr. Zahra Faili, who's been working on this project for about 9 months now, since January. This project is in close collaboration with the BRACE 2 project that there was a presentation on earlier today. And in this project, we are utilizing, any subsurface soil information we could collect, including in-situ testing, laboratory testing, as well as interpreted properties from recorded ground motions toward developing robust soil foundation structure interaction modeling. So this presentation is focused on one of the sites, the Hayward Bridge site, but there are other sites that we will be exploring as project progresses. I want to thank the Peer for funding, and also I want to thank the BRACE 2 leadership team, Professor Musallam and Dr. Amarnath, and also I want to especially thank Crystal and Claudia for their help with our progress. Also, I want to acknowledge SysMip and Caltrans for providing data needed to carry out this research. The Hayward Bridge site, it is located in Hayward area. The bridge has 14 spans, and some parts of the bridge are instrumented. You can see that bend 1, bend 3, bend 4, and I'm going to be referring to this bend 4 frequently throughout the presentation. But what makes this site interesting to us is not only the fact that part of the bridge is instrumented, but the main primary reason we are interested in this site is that there are 2 well-instrumented downhole arrays adjacent to the bridge. The one is the Geotechnical array, very close proximity to the bridge. This is location where the downhole array is. And then there's a second downhole array, the other side. It's called West Geotechnical array. And this is also another site. And we've been utilizing the recorded ground motion and these 2 arrays for the purpose of this project. So a little bit more detail about these 2 downhole arrays. The East array, which is closer to the bridge site, has 4 sets of sensors, from ground surface all the way to the depth of about 300 feet. And through the SysMip website, you can see that there are 3 recording events at this site. The other array, which is a little bit further toward west, goes to the same depth, about 300 feet, but then has more sensors. We have 6 sets of sensors, and there are 12 recorded events at this downhole array. So we'll be using this data in this project. So although we were provided with the shear wave velocity profiles at these 2 downhole array sites, we still utilize the cross-correlation method to calculate the shear wave velocity based on the recorded data. And the reason has been the fact that we wanted to feel comfortable and confident in the data we were given, the VS profiles, and also fill some of the data gaps. You see that, for example, here for the East array. And as you notice, the back-calculated VS profiles, they we're in agreement with the PS suspension logging data. Of course, these back-calculated ones do not have as high resolution as the PS suspension logging, but we were very, pleased with how results came out. So we used the measured VS profile to calculate our maximum shear modulus, and also, we utilize the SPT blow counts from the site using, a couple of existing correlations to look at the variability. So from Caltrans, we had received a lot of the PDF files, including, information about the site, including the information about the foundations and a lot of soil information. We had a lot of the test borings we went through. You see some of the locations of these test borings at this site. They're highlighted, and going back to that bend number 4, So this is, just an example of the subsurface soil, typically stiff clay at the near to the ground surface, and then on top of some weathered rock. And the information, went to as deep as 80 feet, which was sufficient because, typically the foundations were shallower than that. And the site classification also we did, which came as a site class. So in order to establish the dynamic soil properties, one of the steps we took was to calculate the time histories of shear stress, shear strain, as proposed by Ziegel et al. 1995. And so this is where we use those downhole array data and all the recorded events to do this calculation. And based on that, we established the shear stress strain properties at the site. And these data were extremely valuable for us because we could go ahead and calculate the variations of shear modulus as well as damping versus shear strain. Some examples at the East Geotechnical array are shown here. These are all the data from the site. West array, obviously we had more reports, so more data points. But for the sake of comparison, we've added Seed et al. 1986 also curve on this plot. And also the variations of damping at these two locations versus shear strain. And so these data are going to be useful at the later stages of this project. So a little bit about the foundation types. At the two ends of the project, at two ends of the bridge, we have abutments all sitting on pile groups. In between, we mainly have deep foundation, except bed number 2, which is sitting on a spread footing. For the rest, we have drill shafts as well as also pile groups. And the table shows all the sizes and depth and properties of those foundations. So next step for us was to use the subsurface information and also the foundation size information to establish PY model of the foundations. And our modeling included modeling the foundation from ground surface all the way to the bottom of the foundation. So we needed to have the demands from the superstructure or the bridge at the surface. And those information, the forces and shear forces and axial forces and the bending moments were provided to us by the rest of the Brace 2 team, and you see, illustration of their OpenSees model. So in order to establish PY model for this for each foundation, we use our in-house NV program, which is we call it NVShaft, to do the PY analysis. Again, the properties of that the foundation under bridge 4 presented here. The stiff clay, the weak rock, and also the properties of the shaft, and also the loadings were provided to us. Example PY models from the library of NVShaft, for the different depths, these are for weak rocks, and also for the stiff clay, but because of the how small the ultimate P in the stiff clay is compared to weathered rock, I had to do a second plot to show it properly. And then we used 3 different loading cases to do the analysis. More specifically, we used 2 loading cases from 2 earthquakes. And then the third loading case was the design level earthquake, which had a much larger demands. And then, the PY analysis was completed. You see the screenshot of the results from the NVShaft. Typical, PY analysis, which is in nature is sort of, pseudo-static analysis. So in order to make sure our work is properly incorporated into overall Brace 2 team project, we had to, transition to OpenSees. This is where we've been using the data we've already collected, either test borings or repeatable oil counts, or even those dynamic properties back calculated from downhole arrays to inform the properties for these spring and dash plots in the OpenSees model. And OpenSees, in OpenSees wiki, you could find those, the example PY springs for sands. which you see the example here, but in relevant to our project, we are using similar ones, but applicable to steep place and rocks. So our current work involves defining the hysteresis response, because these are the backbone curves of the PY models. We've already have those for different geomaterials in this project. Our current work involves developing the hysteresis behavior, and we've identified two models. Potentially, we will be using those. One is the Masing rule model, as well as the secant stiffness degradation model. So we are in the process of implementing these in our model, and once these are implemented, we will have a proper model. It's a global model incorporating all the soil springs, the shafts and pile groups, and also the abutments, all integrated into one model. And I want to thank the Brace2 team for helping us, implementing these hysteresis models in OpenSees. So with that, I want to thank the opportunity to present and take any questions. I hope I stick on time.
Thank you, Ramin. Any questions? If I can just kind of quickly ask on the stress strain loops, any data that you could then kind of use to validate, what you're getting from these stress strain time histories in terms of your loops?
That's a great question, Ada. The information collected from this bridge goes, is dated, in 70s and 80s. We did not have any laboratory test data to validate our back calculated loops. I wish we had it. It would be, a good opportunity if we could collect data and do those tests. But yeah, that would be really cool to validate our back calculated loops.
Yeah, no, that's understandable. Yeah, thank you.